Hi, hello everyone. Thank you for joining us. Good morning, good evening, good afternoon, wherever you are in the world. I would like to hand over now to Zillard and Richard, who are going to take you through this afternoon's workshop.
Hello, good morning, good afternoon, and good evening, as Deborah said. Welcome everyone. Thank you for joining this Graph Gurus workshop. I'm Szilárd Barany, a Senior Solution Architect in PyTigerGraph EMEA. Today I will show you how to build improved business solutions with graph and machine learning. In our case, we doubled the performance of a fraud detection system. This increase in efficiency was achieved by my manager, Richard Henderson, our lead solution architect in EMEA, whose webinar recording I hope most of you watched prior to this workshop. Richard is also on this call. As he introduced himself, he will support me with answering questions during and at the end of the workshop. Talking of questions and answers, a little housekeeping first. All attendees are muted, but you can ask questions at any time using the Q&A tab in the Zoom menu. As Richard pointed out, it's on the bottom of the screen, of your screen. Of course, this workshop is being recorded and the link will be emailed to you with the slides. An extract of the slides is already shared. You can find the link in the chat window of Zoom. You can use it in case you miss a step during the exercise and you need to go back. And if you have any issues with Zoom, please contact the organizer, Deborah Ives. She is on the chat as well. The exercises will be done using a PyTigerGraph database instance running on PyTigerGraph Cloud. If you have already created your instance, and I hope most of you already did, then please make sure it's up and running. If not, then go to the solution page on PyTigerGraph Cloud and start it. If you haven't created the solution yet, please do so now so that it could be ready by the time you start the exercise, as it takes a few minutes to provision the resources. So if you haven't started yet, please come to the My Solution page, click Start, and wait a few minutes until it starts up. If not, please go through the solution creation steps. Yeah, as mentioned in the email sent to you, we will use two Python notebooks during this workshop, hosted on Google Colab. One will be used to set up your graph in the database around halfway through the session. The other provides the data science content that we will work with in the second half of the workshop. If you want, you can download these and run locally in your Jupyter notebook. Finally, we are going to import data from CSV files. 3 of these will be shared or already shared via GitHub. You can find the links in the chat box. And one is stored in AWS S3 bucket from which we load it directly. So all the links to notebooks and data files have been shared in the Zoom chat. As I mentioned in the beginning, my goal is to show you how to build an improved business solution with graph and machine learning. In our case, our solution allowed to double the performance of a fraud detection system. Of course, your use case will be most likely different, but the concepts and most of the steps will be applicable still. As I'm not a data scientist and I do not have the domain knowledge, at least not at your level, I won't be able to tell you what application to build, but I can show you how to build it. So here is the agenda to achieve that. First, we will review the ways we can work with the PyTigerGraph product and ecosystem. This part will be interwoven by the first dose of hands-on exercises. Then I will review our use case, the fraud detection, and what Richard did and what results he got. This will be followed by the remaining exercises where we will feed the results coming from the graph into the machine learning model. And as usual, the workshop will end with a Q&A session where we can answer all of the questions that could not be answered during the presentation and the exercises. The questions during the presentation exercises will be answered if they are related to that given step. If it's more generic, higher level question, those will be answered at the end. A little introduction first. PyTigerGraph was founded in 2012, and we released the first version of the product in 2015. Our mission is to unleash the power of interconnected data for deeper insights and better outcomes. Graph really is a natural storage and computation model for interconnected data. To get the most out of this, we invented invented the first and only native parallel graph technology. Based on this native parallel graph technology, we are very proud to have the world's fastest graph database and the only scalable graph database for the enterprise. So I mentioned the term native parallel graph technology twice. What does it mean and how did we get here? So let's first look at the evolution of databases. A relational database stores every type of data in a separate table, linking those entries together via foreign keys, essentially a shorthand to remember, for example, the relationship among an order, the products that are part of that order, customer who placed the order, locations where the products are stored, shipped, and received, and suppliers who ship them. Relational databases work well when your schema, i.e. the fields are stable and you don't need to add new fields every day or every week. They can be optimized for high performance for transactions, but there is one area where relational databases struggle. They can't go across a deep network across 10 or even just 5 or 4 hops to do computation analysis. Key value is a type of NoSQL database, and NoSQL databases have existed since the 1960s. The term was marketed heavily in the early 2000s and contains a host of database technologies, including the key value store. As Web 2.0 companies such as Facebook, Google, and Amazon grew rapidly, they needed flexible ways to store the data with increasing number of attributes or fields to model consumer behavior. NoSQL databases such as key value stores offer full flexibility to change schema as needed, and also allow horizontal scaling to clusters of machines very easily compared to relational databases anyhow. But they suffer from 2 major deficiencies. They weren't built for transactional performance, and it takes a long time for them to execute deep queries and analyses. Now let's look at the third column, the graph database. We will discuss the concept soon, but for now, let me just say that they store and analyze both the details of entities and the relationship amongst them. As a third generation graph database, PyTigerGraph addresses the aforementioned deficiencies and limitations with native parallel architecture for loading, for real-time updates, and simultaneous deep link queries going for 3 to 10 hops across the graph with billions of nodes. But these capabilities were not immediately available in the first 2 generations of graph databases. Graph 1.0 technologies such as Neo4j are good for loading up and visualizing small to medium-sized datasets. However, they are unable to load up large datasets measured in terabytes. Also, they are limited in the depth of analytics, tend to time out after 2 hops. Also, their scalability is manual, and scaling impacts the application using the database. Graph 2.0 technologies such as DataSets are built on top of NoSQL repositories such as Apache Cassandra. They solve the data loading problem. You can load terabytes of data into Graph 2.0 technology easily. However, they aren't designed for real-time updates of the graph data. As you have new calls, payment transactions, orders pouring in, it is not possible to update the graph in real time. Graph 2.0 technologies are also poor at handling complex queries that follow 3 or more hops across the network. As the fraudsters and money launderers use increasingly complex multi-layer network of identities and accounts, it becomes unlikely to spot these activities using Graph 2.0 technology. Graph 3.0, third generation of graph engines, were built to address these deficiencies of Graph 1.0 and 2.0 solutions. As mentioned before, PyTigerGraph is one of these, and it is the first native parallel graph. Native means that it uses storage and memory structures and data access methods specifically designed to store graph data. We don't try to squeeze a round peg into a square hole, or more precisely, to squeeze a graph shape problem into a relational or key value structure. Parallel means a distributed, scalable architecture. Production graph instances are typically deployed on a cluster of nodes, each node handling the storage and processing of its share of automatically and evenly distributed graph data. This is also called MPP, massively parallel processing architecture. This comes with the benefit of being linearly scalable. If you need more performance or just want to maintain the existing performance level with ever-growing active dataset, you can do it by simply adding more nodes to your cluster. This is transparent to your applications. They just see a single logical database instance that grows in capacity and performance without the need to modify application code. And I leave it to you to figure out what first means. Now, a very brief introduction to graph databases and graph analytics for those who are completely new to these subjects. A graph database stores and processes vertices or vertexes and edges. This is based on the concepts of graph theory, whose origins can be traced back to Leonard Euler's 1736 paper on the 7 bridges of Königsberg. So the science behind graph processing and analytics is actually older than the science behind relational databases that really started with E.F. Codd's 1970 publication. Vertices are somewhat similar to database tables or data frames in programming languages and data processing frameworks, as in that a vertex, just like a row in the database table or a data frame, contains information about real-life entities like people, companies, products, or even more abstract concepts. But instead of columns, vertices have attributes or properties that could be of simple or complex data types. While a table or a data frame is a main unit of storage in other systems, in TigerGraph, the vertex instances are standalone storage units. Vertices are often visualized as a circle or a disk, although other shapes or even images are also regularly used. In graph theory, they are also called nodes, but that could be ambiguous in computer science, where components of a network or a cluster solution are also typically called nodes, so I will stick to calling them vertices. Edges, to me, are the real differentiators that make graph databases completely different from other data storage and processing technologies. Edges represent relationships between real-life entities, i.e. the vertices. This is the important part, as graph analytics is mainly about discovering and exploiting the value of these relationships that often are not trivial, not direct, that require multiple hop deep link analysis. Through these relationships, a graph database can provide context for the analytics. Utilizing the value of relationships these ways is very difficult, costly, or simply impossible with other technologies. Edges can be considered similar to a join or a primary key, foreign key relationship in a relational database, but there is a significant difference. In a relational database, a foreign key only describes the possibility of a relationship between two joins, and the join construct clause in a query needs to find out if there was actually a link. That is costly. This is why relational data warehouses use a data modeling technique called star schema, which reduces the number of joins. On the other hand, in TigerGraph, the relationships are created at the time the data is inserted and can be seen, and literally you will experience soon, immediately. There is no need for extra work to follow the links. In fact, it is very easy to follow any number of links or hops without any additional work or guessing. This is what we call deep link analysis. We can also say that edges are first-class citizens in a graph database, unlike foreign keys in relational ones. An edge can be undirected, directed, or directed with a reverse edge. Some relationships, like friendship, are not directed, or the direction is not meaningful or relevant. In other situations, though, you need to express a hierarchy or a literal direction, like ownership or events following each other. To ensure that your graph query follows these relationships properly, you want to define directed edges to implement them. But in case you might need to go backwards, for example, to find owners of a property, you might also want to add reverse edges. Edges are generally visualized as a line on an arrow, depending on whether they are directed or not. Edges can also have attributes or properties, just like vertices. And this later feature, having properties or attributes, makes TigerGraph a property graph database. These properties of both vertices and edges can be used for filtering, sorting, and aggregations, and in various built-in and user-defined functions and algorithms. Visually exploring a graph is one of the possible first steps to recognize the often not obvious and long-distance relationships and their values. But operationalizing these findings and insights is the ultimate goal. This can be done by developing queries, which are our kind of stored procedures. They are a piece of code stored and executed in the database at highest possible speed in a parallel fashion and without the need to move the data anywhere. We will see examples of them during the exercise. The four main tools to work with TigerGraph are Graph Studio, a web interface to design, populate, and explore graphs, and to develop solutions. This is what we will use soon. It's the GSQL command line utility that allows you to enter and execute arbitrary GSQL statements. GSQL is the query and programming language of PyTigerGraph, an easy to learn yet powerful language modeled on, as the name suggests, on the structured query language SQL or SQL of the relational databases. We will take a closer look at it later. The next is the REST API that is mainly used for integration and operationalization and aimed mostly at data manipulation and downstream consumer apps. And finally, PyTigerGraph, a community-backed open source Python connector intended to be used for data science and data engineering purposes. And this is what we are going to use in both notebooks. Your TigerGraph instance should be available by now. So let's get started with the Graph Studio. Let me switch to browser. So you just simply click on this actions icon and pick the first item, Graph Studio. It opens a new window, a new tab more precisely. The homepage shows every functionality Graph Studio provides. Let me briefly describe some of these. Designing schema is about setting up or creating your schema or your graph with the vertices and edges. This is the first thing that we will review. Mapping data to graph is about defining data sources and how they should be loaded, how the content of the files or the data source should be interpreted, how they should be loaded into vertices and edges. Loading data, as the name implies, executing the mapping, the data load itself. Exploring graph will be used for looking into the data, finding the insights that will then be the foundation of developing queries, the programmatic approach, repeatable approach to solve problems and execute analytics in the graph database. These 4 items or 4 functionality on the left side, we are not going to cover today, partly because the visual query builder, when you can, using click and drop, drag and drop approach to develop queries, and this functionality which allows you to migrate data into TigerGraph from relational databases. These are already covered with webinars and recordings, and they would take too much time to cover today. And also, we are not going to cover importing and exporting the solution. This is effectively just exporting the metadata of the database, the description of vertices, edges, the graph itself, and so on. This is often used for data used to migrate the schema design, the graph design from development to production, or to replicate or distribute graph design in other databases. So let's look at the actual functionality that we are going to look at today. The first one is design schema. Let's click on this. I hope that you all have your Graph Studio up and running and you can follow me in this exercise. A schema or graph is a collection of vertex and edge types, user-defined types, queries, and other object types. Let's create a simple schema, a person vertex and the movie vertex. And let's create 2 edges, a friend linking person to person, and likes linking a person to a movie. To keep it simple, let's have only 1 attribute for each vertex types, name for the person and a title for the movie. So let's create a person first. Click on the plus icon here to create it. You need to specify a few things for a vertex. First of all, a name, obviously, for the type, which must be unique within vertices and edges. Then you need to specify the primary ID, which has the same function as the primary key in relational databases. It's the value uniquely identifying a single vertex instance. And it could be called anything, but it's quite typical to use simply ID or the vertex type name combined with ID, for example, part ID. And you also need to select one of these available data types for the primary ID. Next, you can style your vertex by selecting a color for visual representation and optionally an icon. Finally, you can specify the attributes. Like in case of the ID, primary ID, you can give them a name and select a data type. Plus, you can specify a default value that will be used if during data loading the value is not specified or not available. You can also indicate if you wanted to index this attribute. Indexing, just like in case of relational databases, improves lookup speed but comes with maintenance cost. So index only those attributes that are frequently used in searches. So let's create a vertex called person with an integer primary ID and a string attribute called name, which will be the only attribute. So let's get started. Person ID is an integer. I leave the color like this, but I pick a person icon for this. The attribute name will be name, which is a string. I don't want to index it, and I don't provide default for you for that. Right. Excuse me. Next, let's create the movie vertex. Again, click on the plus button. Name is movie. ID is an integer. I leave the color as it is. I select an icon. We don't really have a movie icon, but there is a camera, security camera. I think it will do. Camera. And as I mentioned, it will have one attribute called title, which is obviously a string. So far, so good. Now we have the vertex types. Let's create an edge types between them. Let's move it a little bit away. This is done by clicking on the arrow icon. First, you need to click on the source vertex type by clicking on the icon, and then click on the target vertex type the same way. Again, you need to specify a few things for a vertex. It has a name. It can be directed, and if it's directed, you can specify whether you want a reverse H or not. It goes from one vertex type to the other. You can specify the color, and you can specify the attributes. Let's create this likes relationship between a person and a movie. The person likes a movie. It's directional because a movie cannot like a person. I don't need a reverse H here. This person to movie, I leave the color as it is. And let's add one attribute, let's say first watched, which is an integer because I only want to store the year in this. We have a datetime data type if you want to go down to high resolution hour level, which is not necessary right now. Okay, so we have one vertex type. Let's create another one, this time the friendship edge type. It goes from person to person, so I click twice on the person vertex disk. I call it friendship, or I could call it likes, but I already used that for. So it's friendship from person to person. This is the color. I'm not going to change it. And again, let's say integer for year to indicate since how long this friendship is going on. One thing that I would like to mention that I should have mentioned previously is that if you have a undirected relationship, then there is no real relevance between what is the source and what is the vertex type. Not in technical terms. Usually we express still some kind of directionality, even in case of undirected edges. But if it's a directed edge, it's absolutely relevant to know which way you will go most of the time, or what is the only possible way to set up such relationships. So as I mentioned, a movie cannot like the person, but the person can like a movie. All right. So now that we have the schema designed, let's publish it. I make or design permanent database. So far, the design only existed in Graph Studio. Publishing it is done by clicking on this up arrow icon in the upper left corner. It will take a few seconds to persist it. We have now vertex and edge type definitions, but we don't have a graph yet. So let's create one. Create on this global view, and then on create graph. I'm going to create a graph that I call very creatively my graph. And I would like to include all of the vertex types and edge types in this. Okay, create. It will take a few seconds. TigerGraph allows you to create multiple graphs in the same database. This can share vertices, vertex types and edge types, or they can have their own types inaccessible to other graphs. So I'm creating one where I created one graph here called my graph, but I can create another graph which also includes person or movie, or it might include vertex and edge type which is not available on the global level, which is not accessible in my graph. Okay, so we have our first graph created. The little red globes on vertices and edges indicate that we use global types, so something that has been defined in this global view or global scope. As I mentioned, our graph can have its own private vertex and edge types. In that case, obviously, these little globes wouldn't be here. Right. Let's jump ahead a bit now and into graph exploration. We don't have much to explore yet. In fact, we have nothing to explore yet. So let's create some vertices and edges. Again, we can use this plus and arrow these plus and arrow icons to create objects. In case of a new vertex, let's click here. You will be asked to pick the type. We now have two types. You will have to specify the ID and the attribute. So let's play a little bit with this. Let's create a person. Number one is Szilard. And let's create another one. Number two, my eldest son, Albert. Okay, so we have now two vertex instances created, two persons created. So if you move the cursor above this, you can see this pop-up showing the details. It's Szilard, it's Albert. But actually, you can customize the look. And instead of seeing the primary ID, you might want to display the name, making it easier to find out who is who. All right. So now we have two people defined. Let's create one more vertex, this time a movie. Let's say number one, called Star Trek, the first contact. As you can see here, I specified vertex ID 1 here, and I specified the same value for Szilard. But because these are two separate types, you can have the same IDs, they will not mix. The ID must be unique within a vertex type. So now I have three types. Again, let's make it a little bit easier to see. So we have three vertex types. Let's create some edges between them. Let's create the first one from me to this movie. There is only one type that I can pick here. The likes has been defined between these two vertex types. And I watched this movie for the first time last year. Again, let's customize it a little bit. And let's show this value here. First watch in 2020. And then finally, let's create a edge between myself and my son. And his friendship is a valid friendship since he was born. Okay, so we have a very simple graph. But obviously, in a production environment, graph data is not entered manually. It would be too slow and too complicated. This is typically done in initial data exploration or schema design phases when you want to just have some sample data to work with. And I realized that I made a typo here, but I hope you forgive me. So this manual data entry is good for education, training, and exploration purposes. But in production, obviously, load data in an industrial fashion, and then this is what we are going to review now. Oops, you didn't see these. TigerGraph can load and ingest data from a number of sources. The most obvious of these is loading from files uploaded from your local computer, but it's typically done in development and test environments. It is better, faster than manual entering data, but still not industrial scale. I will show you soon how it's done. You can also import data stored in AWS S3 Cloud Blob Storage, equivalent to Azure's Blob Storage or GCP's Cloud Storage. These two are not yet supported, but soon will be. We will load data from an S3 bucket when we will create the graph for the data science exercise. In production environment, it's also typical to load data in a streaming fashion using Kafka. It is also possible to import data directly from relational databases I mentioned earlier. And you can also use the REST API, what will be discussed briefly later, to observe data. And there are plans to implement other data sources, such as the previously mentioned cloud storage services, Hadoop, HDFS, FTP, and HTTP sources. Sorry. What you can see on the screen is your schema. And we need to specify now one or more data sources and then the data mapping. Let's start with defining 5 data sources first. I'm going to use 3 CSV files that I mentioned at the beginning. You don't have to do this exercise, but if you want, you can download these files from the GitHub link that I shared in the chat window and follow me. So the first file is called people.csv that contains a list of astronauts and cosmonauts who actually flew in space. The second file is movies.csv. This is a list of the top 250 highest ranked movies in the Internet Movie Database. And finally, I generated a random pairing between people and movies with a random first watch date. So adding a data source is very simple. Click on this plus button. Click to upload file and navigate in your file system wherever these files are stored. In fact, you can select and upload multiple files in one round. So these are the files that I mentioned previously, movies, people, and the linkage between them. The files are now uploaded to the server. The next thing is to define the file format to tell TigerGraph what it should expect when reading data from these files. There are 5 options that you can see on the top. The first one is file format, whether it's a simple uncompressed text file or compressed by one of these listed methods. This file is not compressed, so I leave it as a text. The delimiter is what is the separator between columns or fields in the data. It is specified as comma, which is correct right now. You can pick other ones. \t identifies tab character as a separator. The third one is end of line. Again, you can pick from a number of options. \n is the typical line and character or characters on your operating system. I'm leave it as it is. It's correct. And the fourth one is enclosing character, which specifies what delimits strings in most of the cases, especially if you import from CSV files generated by Excel. Strings, if they contain the separator character, typically the comma, they are enclosed by double quotes. And in this case, this situation, I exported this data set from Excel, so I specify that some strings might be, for example, this one, which has a comma, might be double quoted. If I select none, you will see that it wouldn't be able to interpret the structure correctly because it thinks that this comma between the good and the bad is part of the structure. Okay, so sorry, double quote. The fifth option is to indicate whether the file has header if the first line contains some column headings, and this is the case here. Okay, so I add this file. Now that you have identified the data source, you can map the data in these data files to vertex and age IDs and attributes. And it's done very simply, very easily. You click on these crossed arrow icons. You first select the data source, and then you select the target vertex or edge type. And then you will see 2 tables on the right. The one shows the columns or fields of the source file with some sample data. And if there is a header row in that file, the names of the columns or fields will be shown here. Otherwise, you will see just numbers for row and or also column numbers here. And on the right side, you will see the IDs and attributes of the selected vertex or edge types. So I will use the rank here as an ID. I simply click on the appropriate column row in the table. And I then select the target, which will be the ID, by simply clicking on that row in the vertex or attributes table. And similarly, I select this title column for these title attributes. And that's it. So it's very simple. Let's map the other files quickly. So the second one I uploaded was this people CSV. Again, the same thing, text, comma separated, normal lines. There are no enclosing characters, I think, but for safety, I picked that. And this one has column names also. The first column doesn't have a name, so you will only see column the _1 here. All right, so I add this. Again, let's do the mapping. Peoples.csv to person. I pick this ID column in the first column as an ID column, and I pick the name for the name, obviously. And finally, peoples to movies. All the settings are correct. These are all numbers, so there is no enclosing character, but it has a header. This time, I map the file to a edge. I simply click on edge. An edge doesn't have IDs, but it is identified by the source and target vertex types and their IDs. So because I mapped the here, map the first column as an ID. I'm going to use this here. So this is this will be the person ID. Similarly, I generated a random number for the movies. I mapped the movie ID to the movie ID and a randomly generated number for first watched. And that's it normally. Most of the time, this is all you need to do, but obviously you can do more. You can, for example, specify various data transformation steps that are executed on the fly during the data load. The summer sign shows what we call token functions. There is a library of functions that could be utilized, for example, to concatenate strings shown here. This is often used to generate composite primary IDs, for example, ones with a timestamp included in it, plus various other things, string, datetime comparison, and data type conversion functions. You can also specify complex filtering options. So for example, if I wanted to filter data column of person ID, or you say a year, only those movies, or only those first watch relationships should be loaded where the year is a actually string. Oh, I might have made it string, but anyhow, where it's sorry, I wanted to pick greater. Where the data column movie here is greater than a value 2005. So now that we have created the mapping, we need to publish it. Again, this mapping so far exists only in the Graph Studio interface. By clicking in this upper row icon, I can persist these mappings in the database. What happens in the background is PyTigerGraph generates loading jobs. It converts these visual mappings into GSQL statements and creates necessary infrastructure to be able to execute these loading jobs. These will be repeated executions most of the time. So we save these as a unit, as a loading job for regular execution later. As you could see here, we can load all kinds of CSV and similar separated value files like top separated values TSVs. But PyTigerGraph is also capable of loading JSON files. JSON is a flexible, technology-independent way for data exchange, but we are not going to cover this today. Instead of this, let's load the data that we have just mapped. Let's click on load data. There is actually not much to do here because all of them was done here. So let's click on this play button, which starts or resumes data loading. Yes, I want to load these files. Data is loaded in parallel fashion if possible. You can pause and resume the process, or you can abort this. And you can even clear the data store. It removes all of the data out of vertex and edge instances, but will not change the schema. Now, important note here, if you load a vertex with the same primary ID or an edge of the same type and same source and target vertex IDs, then the existing instance will be overwritten without warning. This is called upserting. New data is inserted, existing data is updated. This could be a good or a bad thing, so make sure you know what's going to happen. Now the data is loaded. You can have a look at the load statistics. A general statistics is shown here about the amount of data loaded. But if you click on individual data sources, you can see how much of the data was loaded, at what speed, and if there was anything rejected because something was missing or line was oversized or any other reasons. So everything seems to be okay. Nicely, we can see how the number of edges and vertices grew quickly. Right. Now that we have data, let's do a bit of an exploration here. Let's clear what we have previously explored. Yeah, okay, we will have break soon. So exploration. There are a number of ways you can explore or have a look at the data. The first is that if you know a vertex type, sorry, if you know a vertex ID for a specific type, then you can look up that vertex instance very quickly. For example, there is a movie vertex with the ID 25. Bang, Star Wars Episode 4, A New Hope, a classic. You can also get a sample set of one or more vertex types by specifying a sample size and selecting the vertices of interest. So for example, I would like to see 5 of each vertex types. And there you go. Here is a sample. Double-clicking on a vertex displays all edges leading into or out of that vertex, plus the vertices on the other side of the edges. So for example, John Glenn, the first man to orbit around the planet, likes these 5 movies and watched them at various stages, which is unfortunate not to because he died in 2003. You can also expand hops from the current selection, which is signified by this gray outline around them. So I select these 3 vertices. And by clicking on this expand button, I can see my selection. I can say that I want to expand to certain types, edge types, or certain vertex types only. At this time, I just would like to see everything expanded. And here you go. You can immediately see the people and their likes. Let's arrange it a little bit nicer. You can pick from a number of layout types. The force is typically the most frequently used one. So what we can see here immediately is the Handmaiden movie was watched or liked by both Senor Hernandez and John Glenn. You can also try to find paths between 2 vertices or find connections between number of vertices. For example, let's clear this. For example, let's see if there is a path between Yuri Gagarin, the first man in space. His ID I know accidentally that it's 165. And another person, Buzz Aldrin, the first man on the moon with the ID of 10. Okay. Interesting. Will the yesterday show all shortest path? Yesterday, when I was looking at them, I found that there were passes. Let's try someone else, number 11. Okay, I'm not sure why I cannot see the links. Trust me, it works. Moving on, finally, you can use queries to return data. Queries, as I will describe later, we can find you a subgraph, a set of vertices and edges, of the answer to your questions, and their output can be shown here. But as I said, this exploration is just the first step. When the insight and the value is found, it can be operationalized by queries. Okay, before I talk about queries, let's create the graph that provides the background to Richard's improved fraud detection solution. In the email that you have been sent, you will find towards the end you will find 2 links to Python notebooks hosted in Google Colab. These links are also shared in the Zoom chat window. We will use the first one to set up the graph. First, let's open it. You can download it into your environment, your local environment if you want. So let's create a copy of this. Let's save it in our drive so that we can modify and run it without issues. So this is my copy. I close the other one to make sure that I'm not overwriting anything here. So the only task that we need to do here is specify 3 things. One is the subdomain of your Tiger Cloud instance, which, if you follow the suggestions in the email, starts with FRWS, short for Fraud Workshop. My instance is called differently, but I use this instance for various workshop and development exercises. So forgive me the deviation from the recommendation. If you cannot remember the subdomain, you can just have a look at the URL here in Graph Studio, on the Graph Studio page, and copy paste the first part of the URL. So the subdomain is Szilárd Bánai PyTigerGraph Workshop. The next 2 things that you need to specify is the AWS access key and secret key. These you can also find in the email. Let's copy paste these. Make sure that you select only the dark red part. Let's copy the access key here. And let's copy the secret key to the other one. Make sure that when you select it, you select the whole secret key, but not the trailing dot at the end of the sentence. Copy, paste. And that's it, really, what we need to do. When it's done, let's start it. Runtime, run all. While this script is running, while this notebook is running, I am going to describe what's happening here. So the first cell, so active cell, is a link to a GSQL script that is used to actually create the graph instance. As I mentioned earlier, GSQL is a programming language it's a programming language of the digraph database, and it stands for graph structured query language. Let's have a look at this script. As you can see, the first step in the script is create vertex and edge types. And this is how you do it in a programmatic fashion. This is exactly the same thing as what we did when we were creating vertices and edges by clicking and dragging and dropping. This is actually what happens in the background. So in this example, in Richard's graph, there are 5 vertex types. The first one is called merchant. It has a primary ID, which is of string type, and it's simply called ID. It has a field called number of frauds, which is an integer type, and the number of transactions, another integer type. You can ignore the rest for now, those just generalities. Similarly, edge types, Richard created an undirected edge between transactions and categories. Again, because it's undirected, it doesn't really matter which is the from to, but for conceptual, logical, or coding purposes, it's better to use direction which is most frequently used and which is most meaningful for your use case. After the vertex and edge types are defined, just like in case of visual graph creation or visual schema design, we create the graph, this time with this create graph statement. We specify a name and list all of the vertex types and all of the edge types that should be included in that. As I mentioned, you can create indices on vertex attributes, and here is an example of how it's done when it's done programmatically. The next step is to define data sources. This one is an S3 data source, so its setup looks a little bit maybe complicated, but in fact, it's very simple. All we have to specify is the access key and the secret key. I couldn't specify these here because this file is shared on GitHub. And if I publish these keys on GitHub, AWS would disable my account for breach of security policies, sadly speaking from experience. So instead of this, I ask you to specify those values in the notebook, and the notebook, as you will see, will replace these placeholders with actual values. The next stage in the script is loading job, creating the loading job. This is actually the programmatic version of the data mapping that we have done. Here I specify the data source, which is a file called utils.csv in an S3 bucket called TG Workshop 2020-1004. This I'm just reusing the same data file from the previous iteration of this workshop. And here are the data mapping. So I want to load from this data source from this file into the merchant vertex. I'm picking up the 6th column from this file and only populating the ID of the vertex. I'm not loading anything into non-frauds and non-transactions. This will be calculated later. And so on. And you can see here I specified that the separator is comma, there is a header file, and there is a normal \n file. Once the mapping is done, I'm running this data load job. And the final step in this script is creating the queries. I'm going to talk about this a little bit later. Let's go back now to the notebook. In the first cell, I specified the location of this GSQL file. Second step is to install PyTigerGraph. I will talk a little bit about later, but as I mentioned, this is a Python wrapper for the GSQL REST API. I'm importing this into my notebook. This has been nicely installed. This step actually fetches the GSQL script into Python notebook, replaces the access and secret key with the actual values. Next, I establish a connection to the database. And this is where we use the subdomain information specified in the first cell. And then the GSQL script is actually executed. It's already done, and let's quickly have a look at what happened here. So first of all, vertices and edges were created, and from that, the graph was created. Next was the index creation here. Then the data source was created. The data load was started. We can see the progress here. Then the 3 queries were added and installed in the database. So everything is good so far. The next step here is generating a token. I will talk a little bit about later. It is actually some kind of one-time or temporary access key or access password for application to work with the database. We created here. We created this one here, and we will use this value later in the other notebook. And the last 2 steps are initialization steps. The first one is calculating some statistics. And the second one is actually pre-calculating some aggregates. Normally, in a real-life scenario, Richard's schema would receive data in a streaming fashion as the transactions are done online. And he would pre-calculate some aggregations for each of the transactions. And that would take milliseconds. But because we have now, I believe, 600,000 transactions or so, these have to be calculated at once right now. So it will take a while. It might seem to be never ending, but the issue is really just that the Colab notebook cannot detect anything that seems to be running more than 5 minutes. It will be a little bit longer than that. So let's leave it running, and let's now have a short 5-minute break. And after this, we will review what has been created in Graph Studio, and then I will talk about queries as I mentioned. So it's almost 4 o'clock. Let's continue this presentation at 4:05.
Hi, this is Richard. So I've been answering a bunch of questions on the text, doing as much debugging as I can do. Sorry if I haven't given you an exact answer. Certainly, I've gone to I think there's a lot of people asking about the GitHub link. I'm assuming that's for the movie CSVs and things like that. I'll make sure that you get that link later. I'll hassle Szilard if he's still around to do that. Generally, for general questions, please do put them in the Q&A link, because I tend to spot that more quickly. Equally, I know that that can be a little bit clunky, but I'll do my best. We'll work it out. Right. Yeah. So, Connor, that's usually your password is.
Okay, I think I can handle that. Let me show you what needs to be done.
Perfect.
Typically, well, maybe foolishly, I assume that the password that you specified for your notebook, for your graph, when you created it is TigerGraph. If it's different, then you can add this parameter to your notebook. And then this will be used for connecting to the database.
Ah, nice. Or alternatively, you can just reset the password to TigerGraph. It's entirely up to you. Obviously, we wouldn't recommend that for anything other than these demonstrations where it doesn't really matter. There's nothing secret here. Szilard, since you are online, did you have a source for those movies in person.csv files?
Yes. If you look at, let me try to find the chat window. Chat.
Yeah, it didn't turn up in the chat window.
I think it's because you put it in the chat to panelists, Szilard, not to everyone.
Oh, I'm sorry.
I don't think I got it either. I must be out of the loop.
Okay, don't worry. I'm going to include copy paste it right now.
Nice.
Here you go. Every material that we are talking about today, is listed now. Can you see it? Could you please confirm?
There we go. That's perfect. So the people movies and people movies stuff. That's great.
Okay, let me have a look at other questions.
Okay, Rishi, you've got the wrong password problem, exactly the same. I congratulate you on your security approach, but as I say, unfortunately, we were kind of assuming that people would use the TigerGraph password, or you can follow up with what Szilard just showed, where you can actually put the password in as a parameter in the notebook. Through password. Yeah, okay. If we do this in future, we'll definitely put that in. What else have we got? So see, please share further details of the application token when you have microservices or multiple applications accessing TigerGraph. That's an interesting question. So the particular tokens here are specific to the database that you're running against. TigerGraph has an idea of multigraph. And what multigraph allows you to do is to segment the database so that particular microservices would have their own tokens, and that would only be able to access the particular segment of data that they were supposed to see, if that's your query. Generally, we have quite fine-grained approaches to this, and you can generate multiple tokens according to what you need. So if you have loads of them, so if you have loads of services and you want to have a token per service, then you can do that quite easily by just generating multiple tokens. Hopefully that answers your question. Okay. Looks like okay, good. Christine, I'm glad you're on your way. Yes, that password thing is. I think it's catching a few people. Good. What have we got? How would you read from the external file? So there's two ways where you can read from external files. One is you can upload it directly through Graph Studio. That's that's one of the tabs on the left that can upload the files directly onto the server, and then you load it from there. Alternatively, you can load it from S3. And there are documentation on the website. So, must say yes, or rather, yes, we are for a specific example today. So we'll definitely show that particular integration, which is really just a Jupyter Notebook integration, which is really common. Having said that, everything we do in the Jupyter Notebook, you could almost drag that code into any Python file and it will run. So, you know, this is the Python connector, for example, which we're importing, is people do use that all the time in headless Python machine learning context as well. And equally, of course, if you've got anything specific that you want, like a specific problem that you want to solve, then please do get in touch. And we'd be delighted to see if we can help. We're always interested in the integrations and how we can make those better. Okay, I think we've got all the questions. So back to you.
All right, thank you very much, Richard, for your assistance. Let me close these Q&A and chat windows. We have, okay, welcome back. Let's quickly review the graph that we have just created. So going back to Graph Studio, you might need to refresh this. Most of the time it shows the newly created graph, but sometimes you need to refresh it to make sure that it picks up the changes that happen in the background in the database. So I'm picking fraud graph here. Let's have a look at the schema design. This is a fairly simple design. There are 5 vertices defined here. Global statistics, quite surprisingly, will store global statistics, but the rest one is more relevant to the use cases. So we have merchants, customers who are participating in transactions in certain product categories. And as you can see, the edges don't have, some edges have attributes, but it's mostly the vertices that are populated with data. Some of these will use, some of these columns here, especially in transaction, will be calculated by this script that is probably still running. In fact, we can have a look at it. If you click on the admin button in the upper right corner, you can see some statistics about the database, some monitoring information. So it shows the status of various components. It shows the CPU utilization. As you can see, this script is running and will be running for around 5 more minutes. this shows memory utilization, disk utilization, and you can have a look at individual queries. So for example, this fixed statistics query, which was very quick, it was executed once around, I don't know, 10 minutes ago. And this one is not shown here, which is running the aggregation calculation because it's still running. Anyhow, it's still running. Let's go back to Graph Studio. So we have seen the schema design. Oh, sorry, I wanted to pick this one. As you can see, nearly 600,000 vertex have been created. Most of them are transactions, and there are 1.7 million edges between these various vertex types. Let's have a quick look at what data we have. Let's just explore transactions. Let's pick 5 of these. The initialization is still running. This is why we see zeros here. Once it's done, these values, once the aggregations are calculated, these values will be populated. So let's pick one. Double clicking on this, as I mentioned, opens up the first hop neighbors. And so this merchant and this customer engaged in this transaction, the value was $50.43 or whatever unit was used. And the category, the product category was transportation. It might have been a train ticket. Another one quickly. Oh, it's another transportation one between these two guys, and the value was £20.47 or something. Okay, queries. Richard has created 3 queries, and I created another one just to show you later how the queries work. So fixed statistics as fixed aggregations, transaction aggregations are the initialization queries. The main query that we will be using in the data science notebook is this one, which fetches data for a specific number of days. Let's talk about queries now that we have seen these. So queries in PyTigerGraph are what would you call a stored procedure in a relational database. It's a piece of code named, saved, and executed in the database, operating over the data stored in the database. Queries have many benefits. First, they run in the graph, so there is no need to move the data X, for example, to extract data into a Python or R or whatever environment and run it locally. So it saves times and simplifies operation. Second, they can be compiled to machine code at the time when you deploy them. This is what the script did when it installed the queries, so that they can be executed as fast as possible without the need to understand and interpret the code by the database every time it's executed, which is typically the case in generic SQL queries or other graph databases. Third, the query code is executed in a parallel fashion. PyTigerGraph is, as I mentioned, an MPP system, a massively parallel processing solution, meaning that the database might consist of multiple computing nodes sharing the task of data storage, retrieval, and processing. This is transparent to you, no matter if you have only one node in your database or hundreds, the same code runs everywhere. You don't need to know where the specific pieces of the graphs are stored. The system will find them for you. Finally, queries installed in the graph have REST API endpoints so that they can be easily put into production with minimal efforts to integrate them with consumer applications. So for example, here, if I select this get all transaction tabular 3 query, if I click on this icon here, I see that I could use this endpoint immediately. In fact, I'm tempted to use this, but it would take some time. Maybe I will show you later how it works. The data science notebook will actually, through PyTigerGraph connector, will call this function with the right, this RS endpoint with the right parameter. Queries are written in GSQL that you can see here, graph structures query language. So it's closely modeled after the relational databases SQL language, so you will see a number of familiar keywords and keywords and constructs. if you have relational database experiences. For example, this is a select statement here. Of course, due to the unique nature of the graph data structure, some specific modifications, additions needed to be introduced. We don't have time to dive into the language right now, but we have a number of resources from documentation to recorded webinars where you can learn about it. The only thing I want to say now is the logic in GSQL is very simple. You start with the seed vertex set, one or more vertices. Then expand from those vertices into other vertices through edges between them. Where all of those edges traverse and all of those vertices arrive to might need to match certain conditions. Pretty much the same thing that you would do manually in visual exploration. The result of this traversal is another vertex set, which can be then a starter set for the next hop. So this way, hop by hop, you can reach your destination. Let me show you an example. This is a very basic example. In this case, the starter or seed vertex set is all of the customers, all instances of the customer vertex type. The first hop, which is expressed as a select statement, is this one. I'm starting with this source, start seed data set, and through the customer to transaction link, this one here, I want to arrive to transaction vertex instances where those vertex indexes has an amount higher than 100, whatever currency unit it is. So I'm going from here to here, but I want to arrive to only those transactions here where the transaction was more than 100 pounds or dollars. The result, the subset of transactions, is stored in this new vertex set, what I called TRX, and this will be the base of my second hop here. So this time I'm starting with this vertex set, the transactions, the restricted set of vertex transactions, and through the transaction to merchant edge here, I want to find certain merchants where the merchants had more than 10 fraud cases reported. And I would like to see the list of these merchants in an ordered fashion, ordered by the number of frauds they had, with the top victims at the beginning of the list. And this creates me a second vertex, actually the third vertex set. This was the first one, the seed one. This was the TRX is the temporary one, and the third one is the merchant. This is the answer to my questions. These are all of the merchants who were victim to more than 10 fraud cases where the transaction value was more than 100 pounds. And this is printed out, and this output will be a JSON document. I think I can execute this. And here you go. These are those merchants that I was looking for. Here in Graph Studio, you see a visual representation. If I printed some edges as well, if I included the edges, we would be able to see the edges between the merchants and the, for example, transactions, but I didn't want to overcomplicate this. The output actually is not visual. It's a JSON document. This is what your application actually sees. And this JSON document needs to be obviously parsed and interpreted one way or the other. So what you can see here is those merchants that meet the criteria. But obviously, Richard's queries are more complex than this. Don't be afraid, don't be frightened by the complexity. It's actually not that complicated. This is actually a fairly easy to learn language. GSQL is a Turing complex language, which in practice means that it's not just a query language like SQL with select statements. It also contains procedural statements like loops and ifs. You can see some examples somewhere here. For example, here is a for each loop iterating through the results. Here is an if statement selecting, executing certain things based on the condition. These constructs makes the language very flexible, very powerful. So you can actually write complex real program code in it, which of course can be executed within the graph. And we use these capabilities and features of the language to develop a library of fundamental graph algorithms like centrality scores, including PageRank invented by Larry Page of Google, pathfinding, community detection, similarity algorithms, and more. These are ready-to-cook templates that you can easily adjust to your needs and graphs, and you can find them in our GitHub repository. Where did I do? Sorry. Yeah, here. So you can see we have a number of centrality score, example is closeness, PageRank, betweenness. We have classification algorithms, cosine algorithm. We have similarity algorithms, the cosine and the Jacquard, and so on. So these templates can be used for quick adoption for your analytical needs. Queries are typically developed here in Graph Studio, but you can use any developer text editor to write them. In fact, many have them already support for GSQL code like VI, Atom, Microsoft Visual Studio. So there is already a good and growing support for developing GSQL code in your preferred environment. GSQL script developed this way, I mean, using an external editor, are typically executed by the command line utility. Let's have a quick look at that. GSQL command line is a simple command line interface for a database. There is no fancy visualization, development support, just typing and running scripts. But it provides access to all features and functions, even those which are for some reasons not accessible through Graph Studio. It could be used as a developer tool, but it's often used in production environment as a tool to initiate background execution of loading, schema changes, and query execution. It's a Java client, can be run anywhere, even for remote access of the databases. For example, I can use my laptop to run a remote client to connect into a database running in our Tiger Cloud. But this is not the only way you can communicate with the database, or you can actually create queries. I mentioned this Visual Query Builder functionality. Again, I'm not going to show you this in details because it would take too much time, and we have very good presentations for this. It's a no-code query development, so you don't have to write code. You just drag and drop objects and link them together, pretty much the same way that we created the graph or populated the graph. These queries don't need to be installed. They can be executed immediately. But they can be transformed into regular query that then you can further manipulate or customize. And then when you install this immediately generates an endpoint, so which can be used then external systems like Python. So it's a very, very quick path from exploration to operationalization without writing a line of code. I talked about REST API a number of times. This is a very important and very powerful interface to the database. It's a programmatic interface, HTTP endpoints returning JSON responses. In fact, as you could see here, this is pretty much what you get in format, a JSON document. And it covers all kinds of functions: observing, retrieving and deleting vertices and edges, running, executing installed and interpreted queries, working with metadata, authentication, additional functions, a lot of path-finding functions. A lot of things can be accessed. But if you are, let's say, a Python user, this might be too much of a hassle to work with this data. Because mostly it is executed from a browser or using the curl or wget functions, but specifying URLs, especially if you have to post a request, is complicated. Most modern languages provide some way to communicate with REST APIs via HTTPS. It's more convenient. But it's still inconvenient, slow, and error prone if you have to handle each of the requests yourself manually. So this is why we started to develop language connectors, and this is where I finally get to PyTigerGraph, which is a Python connector for TigerGraph. It started as a community initiative, but TigerGraph is now contributing most of the solution. It's not officially supported, but you can get help on the community website. In fact, we have this available in our open source repository. You can easily either check out the code or you can install it using pip. We have a documentation provided for this. And then we have also the developer website and the community portal where your question regarding PyTigerGraph or anything TigerGraph related can be answered, and very surprisingly and very nicely, not just by the TigerGraph team, but other users are contributing to answers. So coming back to my slides. So it is essentially, or at least it started as a wrapper over the REST API endpoints, but it grew a lot more. Now you can have access to all of the GSQL commands, and we are currently developing nice wrappers to make it very easy and very efficient to work with TigerGraph database from Python. The purpose of this interface, PyTigerGraph, is to bring graph analytics results into TigerGraph. Please don't use it as a tool to extract data from TigerGraph. Don't use TigerGraph as a Bitbucket. Let TigerGraph do the heavy graph analytics and use those results to enrich your Python model. This is exactly what we are going to do in the next few minutes when we will have a look at the data science notebook. You can use it in the Jupyter Colab notebooks and visualize your findings. There are other language connectors in development. There is a JavaScript being developed right now, and partners develop C# and Ruby connectors. We are looking at next stage, Java, R, Go, Rust, whatever the most relevant connector for our customers. Finally, let's talk about this use case, the fraud detection use case. I hope that you had the time to watch the recording of the presentation by Richard. For those who couldn't watch it, here's a very brief summary. So Richard was using a public data set and built a machine learning model based on fraud scoring application to validate that using TigerGraph gives materially significant improvements. The results needed to be explainable, and the data and the method needed to be replicable. Runtime performance should be the same or better than the legacy solution. And he wanted to minimize rocket science, maximize data science. The initial outcomes show around 50% increase in frauds detected with a 60% reduction in false positives. The key behind this improvement was the real-time generation of new features from the graph. As I mentioned earlier, this would have been generated in real situation every time when a new transaction arrives in, but because we have the batch loading, we have to generate this data in one round, which is what took a little bit longer. Generating these additional features would be difficult, too long, or impossible using other technologies. As you saw, where is it? The Schema designed a few verticals describing these retail transactions with customer buying products of certain categories from merchants. Using the information loaded into the Schema, Richard was able to generate these new features in real time over the parameterized history of days. A feature generation is just one of the ways TigerGraph can support machine learning, deep learning, and AI. Additionally, it can be the perfect platform for certain machine learning or deep learning methods, for example, neural networks, which are fundamentally graphs. And also, TigerGraph can provide background for explainable AI by providing ways to map the decisions made by the AI system into the graph. And there are certain cases when these kind of new features are not available. For example, one of our customers, a huge telco, is using graph features to enrich their fraud detection model, and they can take into consideration, like, how many calls you have to friends and how many of those were answers. Because if you have such calls, you are probably not a fraudster, but people who have only outgoing short calls never receive calls and they don't have a stable group of friends, they are probably fraudsters. All these features are very difficult, impossible to find or generate in other sources, but in graph, these are very easy to find. And the results were quite convincing. So without any Predator, there was more than 1,000 frauds undetected, and there were no false positives identified. With a simple basic classifier on transactional data, this went up when the undetected frauds went under 300, and more than 100 false positives were detected. But using the history, using these features, these additional features, Richard were able to halve the undetected frauds and have 60% better value for false positives. And the results are explainable. As you can see, using real-time aggregates and graph context, there is a more detailed picture of what really influences fraud detection. And even you can find more relevant features than you could find in using just transactional data. So let's bring all of this into the notebook. In this email that you have been sent, there is another link for this other notebook. Let's open this up. And again, let's create a copy to make sure that we are not overwriting anything. I close this one. So to be able to run this, we need to provide two things. And let's start with those two things. First of all, again, we need to provide the subdomain of our instance so that the notebook would know which the PyTigerGraph instance to be connected to. So as I mentioned in my case, it's SVTG workshop. And we need to provide the token that I was talking about, the session level one-time access permit that has been generated in this step of the previous notebook. So just simply copy paste it over. And that's all what we need to do for now. Once you have provided these details, we can go into runtime and run all of this. And while it's running, I'm describing you what's happening. So again, the necessary modules are installed, and then they are imported. This is where the actual database interaction is happening. Again, we open a connection to the database, and this function that we saw here, the get all, this query actually, this get all transtabular 3 here is executed for 14 days. Once the data is fetched, it's turned into a data frame. In fact, it's turned into data frame, and then we will see what's being loaded. It takes around 1 minute to load the data. In the meantime, just for safety, I checked that the pre-aggregations has been done. Yes, the main, this long-running transaction has been completed. Okay, we should see the data coming in anytime now. And here you go. As you can see very quickly, 600,000 rows of data, enriched data with new features. All of these columns came in. As I said, I'm not a data scientist. I can't fully explain the rest of the steps. But what we can see here is that after going through all of this data manipulation, we get these results that we have seen. This is the one without any predictor, just the data itself. If Richard uses the transactional part, then we got the results is better, but not really the best results. And when the using the cut boost classifier, when Richard reaches the point where the newly generated features of the graph is taken into consideration, we will see this third matrix with the improved values. While it's running, let me grab the opportunity to show you a few links. If I can find my where is my, oh, here it is. So we can, let me show you a few links. So I mentioned we have a community forum. that you can find all kind of information, operational data science questions, either from us, PyTigerGraph team, or from our customers and users. We have a community chat on Discord. We have a developer site, and we are on most of the social media sites. YouTube is really good. We have a great number of videos on GSQL and a number of, I think, nearly 50 Graphs Guru sessions recordings. And obviously, we have our GitHub. This is the official repository, and this is the open source repository. And coming back to this, it's still running, and I'm afraid it's running out of time, but it should be done soon. And yes, here we are, and we can see the final results. And this is what's going on. Obviously, I cannot really tell you what kind of machine learning or deep learning or AI functions you should or you could use for your use cases. But the real important thing here for me was to show that it's very easy to integrate graph functionality and graph-enriched data set new features into your notebook or into your analytical work. It's really easy to develop queries in TigerGraph, go through large volumes of data, get the new features, calculate something that cannot be calculated otherwise, and bring it into your notebook or other analytical methods, whatever technology you are using. And I think this is the time to go into Q&A, and Richard will help me to answer questions. Richard, are there any questions that couldn't be answered?
Richard has actually had to drop off the session, but there are actually no outstanding questions at the moment. I think everything's been taken care of, unless anybody has anything else that they'd like to raise.
Obviously, we will be available for answers either through the community portal, or you can ping me directly if you have any questions. I will try to answer that question or connect you to someone who can provide you with help. There is a question, is there an export to the graph created here? No, I can provide that easily if that's a requirement, but I think it would be probably better to just replay this. If you want to create a copy of this in your local environment, you can replay these actions. But actually, you know what? I'm going to provide the export of the schema for you after in the email that I'm going to share soon.